Good evening, everybody. Welcome to another night of a Santa Fe Institute lecture, public lecture. Marvelous to see such a good crowd, especially with a storm blowing in the middle of winter and so on. First I want to give some acknowledgements. The lecture is supported very generously by the McKinnon Family Foundation, with added support, of course, from the Lenzik and from the Santa Fe Reporter. And we're very, very grateful to all of those for giving the kind of support that we need in order to bring these kinds of lectures to the Santa Fe community. My name is Jeffrey West. Yes, please, please. My name is Jeffrey West, and I'm on the faculty at the Santa Fe Institute, and I'm really delighted and have the honor to introduce tonight's speaker, Sean Carroll. Sean is on our external faculty and is also a what's called a part of our fractal faculty, which is a part of these are people that are invited to become part of the Santa Fe Institute who are particularly distinguished. So we have many very distinguished people, one of which you will hear tonight, Sean. So Sean is a physicist. His pedigree is through Villanova University as an undergraduate, and then Harvard as a graduate student in astronomy, where he did his thesis on cosmology, gravity, astrophysics, and so on. And that has sort of permeated his career. He's had a very distinguished career in areas associated with that, but dealing more and more with fundamental questions. And that, of course, is going to be the main theme of the topic tonight as he discusses quantum mechanics. After his PhD at Harvard, he had various postdocs. He was on the faculty for a while at the University of Chicago, but for the past many years, he's been on the research faculty at Caltech and has just left there to take a very distinguished chair at Johns Hopkins University. I don't know if it was on the, yes, there we go, Johns Hopkins, as a chair of natural philosophy with appointments in both physics and philosophy, just to give you a sense of the breadth and depth of thinking that Sean brings. He's maybe well known to many of you because he's a prolific writer. He's written 4 books, and I'm going to read the names to you because they sort of summarize some of the main interests and contributions that Sean has made, and they're cute titles, I must say. One is From Eternity to Here, which is about the arrow of time. Second book he wrote was The Particle at the End of the Universe, about the infamous Higgs boson, and we just celebrated 10 years since the discovery of the Higgs boson. Third is the big picture on the origins of life, meaning, and the universe itself, about ontology. And the last, Something Deeply Hidden, about the foundations of quantum mechanics, which we'll hear about tonight. And of course, you presumably wouldn't be here if you didn't know what quantum mechanics sort of is, that it's foundational in terms of physics. It's been almost 100 years since it was developed in 1926, 27. And it's been incredibly successful, enormously successful. It underlies many of the things that you're familiar with, like lasers and materials and superconductivity and so forth, enormously successful. But also it's brought a bunch of paradoxes. And maybe the biggest paradox is that we still don't really understand at the deepest level what it means, or what some of those symbols that we use actually are manifesting. And I thought what I would do is, just before we let Sean take the stage, is read you a few quotes because of famous people that you have heard of make their statements about quantum mechanics. I mean, because the two major things that quantum mechanics brought that shook the world, at least the world of physics, well, one, it introduced the fact that things seem to be probabilistic, that there was a probabilistic, stochastic element to fundamental questions of physics. And secondly, the role of the observer. Somehow we had to be involved in the measurements to make sense of what quantum mechanics was about. That is, it brought a certain degree of subjectivity to it. So in terms of probability, Einstein made the famous comment, God does not play dice with the universe. Often in terms of this idea that it was this kind of weird subjective, the idea that there had to be an observer, came an extreme statement. For example, I got one here from Martin Rees, who was the Astronomer Royal of the United Kingdom. The universe exists because we are aware of it. So all of this is somehow a construction of the mind. And Einstein had already made a statement in refuting that by saying, do you really believe the moon is only there when you look at it? And finally, two things. One is from Richard Feynman, who said, if you think you understand quantum mechanics, you don't understand quantum mechanics. And Schrödinger, who was one of the great founders of quantum mechanics, who said, I don't like it, and I'm sorry I have anything to do with it. So with that, let's hear from Sean, and we may have an historic moment when indeed all these questions will be resolved. Sean.
Thank you, Jeffrey. Thank you to, are you hearing me? Is that true? You're not hearing me? You are hearing me now? Very good. Thank you, Jeffrey. Thank you, everyone at the Santa Fe Institute for inviting me and everyone in Santa Fe for coming out. It occurs to me, this is a picture of one of my cats. Her name is Ariel. I hope you get the joke. You quantum mechanics aficionados will get the joke of the picture here. Ariel's brother's name is Caliban, which I only bring up because they're named after characters from Shakespeare's The Tempest, which reminds me of the weather that is going on in Santa Fe here right now, which is doing its best to be tempestuous. So I'm especially thankful to all of you to coming through the downpour to get here. And I've given a talk about this subject many times before, but I did try to make this one different. I'm going to try out some new material on you folks, and so I hope to get some feedback on whether it works. And I thought I would start just by giving it away. I'm telling you the punchline, okay? Because it's not like a magic show where I tell you a bunch of things and then at the end it's a surprise. I want you to really understand quantum mechanics. And I have to say, as lovely and as appreciative as I am about Jeffrey's introduction, the Feynman quote is fake news. He never said that. He did say, I think that nobody understands quantum mechanics. That's what he said. He didn't say if you think you understand it, you don't. He said no one understands it, whether you think you do or not. But what is important is that it is understandable. And some of us think we do understand it. We may or may not be right. But even if we're wrong, it is not magic. It is physics. It is science. And it can be understood. So just to rub in what a large ask I'm making of you here tonight, I have a picture here of the universe. It's zoomed in to a little tiny part of the universe, and it's supposed to remind you of how we often think about reality, about the world. Namely, it's made of stuff. There's a chair, there's a book, there's a floor, here's a podium in front of me, and it's arranged in space, right? The podium is to my front, I'm behind it, and so on and so forth, and that's the world. That's the world we live in, and the job of physics is to explain it. Quantum mechanics, I'm going to claim, says no. That is not what the world is. When we look at the world, we don't see the entirety of reality. Reality is much richer than that. And in fact, what reality is, I'm not going to keep it a secret, is a superposition of many different ways that stuff can be arranged in space. And don't worry, I will tell you exactly what is meant by all of those words. But the great thing is that reality can be divided up into subsections, each of which acts like a world comprised of stuff arranged in space. So the crucial thing here is that you're not saying that reality is a bunch of things in space. Space is one of the things in reality, and there's many, many other copies of space in reality. Now, that's a big ask. That is a lot to swallow. You should not just take my word for it. So what I want to start to do is I'm going to sneak up on you. I'm going to say a bunch of things based on, historical, real experiments and thoughts and so forth, and you're going to be going, and then at the end I'm going to realize what it all means, and you're going, oh no, I don't like that anymore. So that's where we're going to go. So it starts over 100 years ago, and we've seen this picture, right? On the right here of the atom, classic picture. Physics departments use it as their logo and so forth. The Rutherford atom, it was put together around 1909. It looks like a little solar system. You have a nucleus in the middle, electrons spiraling around it. Even though this is an iconic picture that is still thought of as the symbol of physics or atomic energy or whatever, it was instantly known to be false as soon as people suggested it. It can't possibly be right. And the reason why is, it looks like a familiar thing, the solar system, but those electrons are moving very fast if you plug in the numbers. And when you take an electrically charged particle like an electron and you move it, like in a circle, it gives off radiation. It gives off electromagnetic waves. The electromagnetically charged particle has an electric field that is trying to point to it, and if you move it, the field has to shift, and those shifts ripple out at the speed of light, and we call them light. That's what they are, electromagnetic radiation. So if this were what the atom was like, it should be giving off radiation very, very quickly, and you can even do the math. You can ask, how long would it take for those electrons to lose energy and to spiral in and just settle down there where the nucleus is? The answer is 10 to the minus 11 seconds. Okay, 1/100th of a billionth of a second. So we can do the experiment there. We did it. This is not what happens. This prediction is that all of ordinary matter is wildly unstable. An atom should collapse if this were the real atom that the real universe was based on. So something is wrong about it, and they knew that right away. They knew electromagnetism and so forth. Now, it took a while. I'm skipping some steps here. It took a while to figure out what was going on. Separately, people like Max Planck and Albert Einstein had suggested that light, which is a wave, had particle-like properties. So to solve this problem, people like Louis de Broglie suggested that maybe particles, like electrons, have wave-like properties, that they really are more like waves than like particles. And what happens then is that rather than having an orbit around the nucleus, the wave that is the electron has a shape. I say wave, but it's really a field of some sort that can take various different shapes. If you were in a chemistry class in high school or college, or are a chemist for that matter, you know about the orbitals that electrons can have in atoms. Those orbitals are just ways that the electron wave can settle down. And none of them are all concentrated right there in the nucleus, because that would actually take a lot of energy. There's a minimum energy state that it wants to go in, but if you have a lot of electrons, they start filling up the other levels as well, and therefore you have chemistry and the periodic table and all these wonderful things, okay? Notice that nowhere in here, this is the beginning of quantum mechanics, but nowhere in here that I say the universe is made of little discrete bits. That is not what quantum mechanics says. If anything, it's the opposite. The universe is made of waves, but when you solve the equation for the waves, you find that the waves take certain discrete shapes. And that's where the word quantum comes from. And very quickly, after this idea came along, people did the obvious thing, which is they found an equation for the waves. And this is known as the Schrödinger equation. There will not be a quiz, don't worry. The point is that you do need to understand that big Greek letter psi, that where it says for wave function psi. Psi is the wave function, a really dopey name for a very profound idea, but we'll be talking about it a lot. Schrödinger came up with this equation that says how the wave function of the electron or of anything else changes over time. And it basically says the amount of energy in the wave tells you how fast it's changing with time. So physicists love this. This is looking really good, okay? Physicists already in the 1920s, they loved waves because they knew about electromagnetism, which are electromagnetic waves. That was very familiar. And they certainly love equations because then you can assign problem sets to your students, and that's what physics is being all about. So it was all good in 1926, but then someone pointed out the obvious lurking problem with this, which is that physics is based on observations and measurements, data that you collect. And when you look at electrons, you don't see waves. You see particles. Here's a real image, a real little movie. This is a radioactive source in a cloud chamber giving off particles. It's radioactive, so it decays. It can emit particles, and you can use the Schrödinger equation to predict what the particle wave functions should look like, and the answer is they come out as a big spherical cloud moving in every direction. That is not what you see in the picture. All of these little lines are individual particles being emitted by the radioactive source, and they leave a straight line trajectory, like they're a particle with a location moving away from the source. So this is very strange. We're saying that to explain the structure of atoms and matter, we need to imagine that electrons are really waves, but we never see the waves when we look at them. This is the beginning, as Jeffrey mentioned in his introduction, of the quantum weirdness that we need to talk about what we see. No other theory of physics ever needed to do that. This is why quantum mechanics is hard. Maybe it's difficult to measure things in classical mechanics, but you can always do it in principle to whatever accuracy you want. But in quantum mechanics, as soon as you start trying to make sense of things, it's almost as if what you're saying is that electrons behave like waves when you're not looking at them. But when you look at them, they start behaving like particles. Now, this should drive you crazy. You should be getting itchy. You should be like, that doesn't sound like it makes sense to me. What does the electron care whether I am looking at it or not? It's an electron. It just does its electron things. So this is very upsetting. It seems to sort of in a kludgy way fit the data, but it can't be right. So what do you do? What do you do about this sort of crisis in understanding what's going on? So what we did almost 100 years ago is we assembled the world's greatest minds, the smartest physicists that we knew, assembled in Brussels in Belgium for this Solvay conference in 1927, the fifth Solvay conference. This is one of the best and brightest collections of people ever assembled in one small room. Half the people in this picture won the Nobel Prize or would win the Nobel Prize soon. Marie Curie, who you can recognize there, she won 2 Nobel Prizes. You have to be twice as good, as many of you will know. But you have Einstein, you have Bohr, you have Dirac, you have Schrödinger, you have Heisenberg, all the big names in quantum physics. Got them into a room, they talked, they had a few Belgian ales, they thought about this problem of, it seems like our best theory of the world says that electrons behave like waves when you're not looking at them and then like particles when you are. What can possibly be the deep hidden truth behind this? And at the end of the week, they came out and they announced, okay, we've got it figured out. Here it is. Electrons behave like waves when you're not looking at them. And they behave like particles when you are. That was the resolution. They bit the bullet. They said, that's it, moving on. All of our deep questions have been answered. And that became the consensus view. When I say consensus, there were some objectors, Einstein and Schrödinger also, they never believed this. They both objected to this point of view. I actually want to say something about Einstein because I'll say 2 things. Number 1, he was a smart cookie. Maybe you've heard that before. It's true. But number 2, if anything, Einstein is underrated. There's this myth that goes around that, in later years, Einstein became kind of a conservative, old fuddy-duddy. He couldn't keep up with the new quantum hotness, and so he sort of was relegated to the sidelines. That is entirely wrong, historically. For one thing, Einstein, when this picture was taken, was younger than I am now, so I refuse to describe him as an old fuddy-duddy. But also, Einstein, number 1, did as much as anyone, literally, to help invent quantum mechanics in the first place. That's what he won the Nobel Prize for. And number 2, even later years, he understood quantum mechanics at least as well as anybody else. What he didn't do was accept the hectoring that he got from the rest of the participants saying, all the questions have been answered. To Einstein, quantum mechanics was a step in the right direction, but it wasn't finished yet. And the thing is, he was right. He was completely right about everything he said in these arguments, but he lost the public relations battle, okay? So you know that when you're Einstein and you can't convince your fellow physicists, it's an uphill battle. The story that was promulgated after the conference was this kind of recipe for dealing with wave functions in quantum mechanics. You have a wave function, capital psi over here, some spread over x and y positions in space, and then there's a black box that you plug it into. You say, what happens if I observe, if I measure the position of the electron? And the answer is you can't predict exactly what you will see, but you can predict the probability that you will see the electron in a certain place. You always see it in a certain place. You don't see the wave, you will see a particle. The probability of seeing the particle at any one location is given by the pre-existing wave function at that location squared. Okay, so where there's more wave, there's more probability for seeing the particle. So again, uniquely in the history of physics, we have two sets of rules, to describe quantum mechanics. One set of rules for when you're not looking at it. Systems are described by wave functions. The wave functions perfectly obey Schrödinger's equation. Then when you measure them, a completely new set of rules takes force. And again, that never happened before in physics. The wave function will collapse to a particular value. It will look particle-like, and there's a probability that you get different measurement outcomes. So this is known as the Copenhagen interpretation, but people disagree about what the Copenhagen interpretation actually says, so I just call it the textbook version of quantum mechanics. I'm not fooling you, for those of you who are not physicists. This is what we teach our students at Johns Hopkins or Caltech or anywhere. This is what we tell them about quantum mechanics. If they start asking questions, we kick them out. You laugh. Nervous laughter. The reason why you should be a little bit upset about this is because the textbook picture of quantum mechanics is clearly unacceptable as a fundamental theory of nature. We'd like to think that quantum mechanics is the best, most fundamental, most basic idea we have about how nature works, and yet we tell this crazy story about what's going on. So let me highlight two ways in which this is unacceptable. And again, by unacceptable, I don't mean false. I just mean clearly not the final answer. Clearly there are some questions being left open here. So the famous one is the measurement problem. So in those rules for quantum mechanics, we have when you observe the system, you get certain things happening. What does that mean? What counts as a measurement? Can a video camera measure something? Can a mouse measure something? What about a person who needs glasses? And they don't have their glasses on. What if I just squint at the system? How quickly does it happen? When does it happen? Why does it involve, a conscious kind of observer? And you can see how a whole book industry about quantum healing and quantum yoga and quantum leadership is going to spring up in the aftermath of this, because this way of talking seems to put human agency at the center of the universe in a very non-Copernican way. But whatever the answers are, the point is the Copenhagen interpretation doesn't tell us what the answers are, and that is too vague to be the final answer to a theory of fundamental physics. Then there is the reality problem, which different people also have different angles on. So we talk about the wave, the electron wave, or the wave function, as we call it in the post-Schrödinger era. What is that? Is it a real thing? Like an electromagnetic wave, it's a real thing. You can measure it, you can put a little magnetometer or a charge, and you can measure where the electric field, magnetic field are pointing. But we said you can't measure, you can't observe the wave function. It's never what you see. Is it real, or is it just a way of making predictions about reality? And you can see how it's going even further in the spooky woo-woo directions. It's almost like we're bringing reality into existence by thinking about it or looking at it or other bad things that lead to bad movies and bad TV shows, okay? But it should be science. So we should think about this and we should be able to answer these questions. Let's think about the reality problem. Let me admit that for all these questions, not everyone agrees. So I wrote an op-ed piece for the New York Times where I say, nobody understands quantum mechanics and that's a problem. And I expected at least a few of my colleagues to email me saying, what do you mean? I understand quantum mechanics. And I was pleasantly surprised it was only one colleague who did email me about that. But the point is that people don't agree within the field. So even if one of us is right, there's no consensus among physicists about the answers to these questions. So from to this point to this in the talk, I've been saying things that are true. I hope I'll be saying things true in the future, but I'm going to be more opinionated. I'm going to give you my angle on it. It needs to be a 6-lecture series for me to give you everybody else's angle on it, so you can invite them to give you their pictures. I want to talk about the reality problem. What is the wave function? Is it something real? Is that what the real world is? Is it like a wave function? Or is it just a tool for making predictions? The answer is it's real, in my view. Again, not everyone agrees. Here's the evidence, the famous double slit experiment. There's other pieces of evidence, but this is a good famous one. Let's say you have a wave, and this was actually an experiment that was done in the 1800s for light, to show that light was a wave before we knew, because Isaac Newton thought that light was a bunch of particles. Maxwell said it was a wave, the wave theory won out. Thomas Young took a light and he pointed it from a source at a barrier with two slits in it, two openings. And then if it is a wave, that wave should appear on the other side of the two openings in a spherical pattern. So it's almost like two different waves are coming out from the two different openings. And then what you get is interference. So because there's two different sources of the waves, some places the waves will combine and reinforce, other places they will have opposite signs and they will cancel each other out. So what you see in the middle there is an interference pattern, bands of light and dark, if a wave passes through those two openings. In quantum mechanics, what you predict if you pass a single electron through those two slits is that the electron, you're not observing it, you're not measuring it, you're just letting it go through the two slits. It acts like a wave, and therefore you should see an interference pattern. The thing is, when you detect it on the screen, you're detecting it. There you are measuring it, so you just see a dot. And a dot is not going to show you an interference pattern. But what you can do is just send one electron through, and then another one, and then another one, and then another one. And what happens is what you see on the right, that's real data, you see interference patterns emerge. So even though you're sending in the electrons one by one, and they kind of behave like particles when you observe them, along the way, they behave like waves. They interfered. It's hard for a representation of our ability to predict future experiments to interfere with itself. Real waves interfere with themselves. Real waves go up and down and can cancel each other out. This is exactly the behavior you would expect if the wave function were something real. So, you can wriggle out of this. Physicists are very clever. They can wriggle out of anything. But let's not work too hard yet. Let's just go with what seems to be being suggested by the data. The wave function is a real thing. You're willing to go with me on that. Sure, the electron wave function is a real thing. I mean, it holds up the podium, right? Because the atoms have shapes because of the electron wave function. Well, there's a complication that was invented by, guess who? Albert Einstein and his collaborators, still thinking very profoundly about quantum mechanics. They invented or popularized this idea called entanglement. Einstein, Podolsky, and Rosen, 1935. So consider a particle, and let's just think of it as a particle right now. We know it's really a wave function, but that's okay. If it's a very heavy particle, it'll just sit there. But it's an unstable particle, like an unstable nucleus or a Higgs boson or something, okay? Imagine this particle can decay into two other particles. And you can predict exactly what's going to happen. You can use the Schrödinger equation. Quantum mechanics, despite its conceptual murkiness, as far as making predictions is concerned, it's incredibly precisely quantitative and successful. So you predict that the unstable particle decays into two particles, but you also predict that those two particles have wave functions. So they don't move off on an individual track, they move off in these spherical clouds. That's the prediction that the Schrödinger equation makes. And that's fine, that's good. But then you're going to measure. You're going to observe. You're going to ask, well, what direction do I see the particle coming out of, right? And this is what we actually do at the Large Hadron Collider, at Geneva, and so forth. We measure particles coming out of collisions and decays all the time. So what you will see, if you look for particle number 1, let's say, you'll see that it's moving in a certain direction. You don't see the wave, you see it looking like a particle. But now notice that the original particle, the blue one, the unstable one, wasn't moving by construction. So it had zero momentum, it had no motion. And momentum is conserved. Therefore, if you see one particle moving in one direction, the other particle has to be seen moving in the other direction because the two final decay products must also have zero total momentum. They have to be moving in opposite directions to cancel each other out. And what that means is that even if you had just observed particle number 1, you would instantly know what direction you were going to measure particle number 2 moving in, even if it was really far away, even if you waited a really long time. This bugged Einstein, but who cares? Who cares about what bugged Einstein? We just want to think about what it means for us. We accept this as real. Somehow, and this is true if you can do this again and again. You measure it again, measure particle 1 in a different direction. Particle 2 will always be moving in the opposite direction. You can do this over and over again, however many times you want. What is going on? It can't be the case that particle 1 has a wave function where you can predict only what direction it's going to come in with a certain probability, and particle 2 has a wave function, you can only predict its thing. Somehow there's a connection between them. That's what entanglement is. And the answer at the level of the symbols and the equations is perfectly clear. Entanglement implies there is only one wave function, even when you have two particles. It's not that you have a wave function for particle 1 and a wave function for particle 2. You have a single wave function that depends on both where you will observe particle 1 and particle 2, or what their momentum is, or whatever you want to observe about them. So if you think here, this is not a great plot because I just plotted a similar thing meaning something different, but here is the positions that you could measure particle 1 and particle 2 in. There's a possible wave function of it. So what the wave function is doing is assigning a number to every possible location that every particle could be in. And this is not just for two particles. If you have the whole universe, you would have a wave function of the universe. And what is the wave function of the universe? It assigns a number to every possible configuration that everything in the universe could be in. And you square that number and you get the probability of actually seeing the universe in that configuration. So the point of this discussion is there's only one wave function, and therefore the wave function is a little bit different than the waves that you're used to, like the electromagnetic wave and things like that. It's not a wave propagating in ordinary three-dimensional space. It's not like one wave for particle 1, another wave for particle 2. The wave function doesn't live in 3D space. It assigns a number to every possible configuration of everything in the world. Okay? That's a different kind of thing than the classical waves that physicists had been so happy about. Now, if you didn't object when I tried to convince you before that the wave function for a single electron was a real thing, it acted wave-like, it interfered through the slits and so forth, then you can't object now. I just put more particles in, okay? The wave function is just as real now. But the wave function is an assignment of possibility to every possible way that things in the world could be. And you said the wave function is real, and therefore, quantum reality is not a bunch of particles or of waves living in good old ordinary three-dimensional space or four-dimensional space-time. It's a superposition, which is to say a combination of all at once of all the possible ways that everything in the universe could be arranged. Now, maybe the amplitude, as we call it, the number psi, is 0 for certain configurations. And then we would say there's 0 probability of seeing that. But still, there could be a non-zero probability for lots of things. And if you think this is real, then what you're saying is reality is way bigger than we ever thought it was. We look around and we see chairs and podiums and people and things like that. This is only one realization of what is really going on in a much, much bigger reality, according to quantum mechanics. Nobody said this in 1935. It was an instant conclusion you could draw from what was said in 1935. Erwin Schrödinger sort of joked about it a little bit, but he didn't quite follow it through. It was left to a graduate student 30 years later, 20 or 30 years later, Hugh Everett, to figure things out. And Hugh Everett basically said, you've just been working too hard. Like this story you're telling, it's okay. That's why I've labeled it quantum therapy there. He didn't add any equations. There's no Everett equation. There's no Everett model or anything like that. All Everett did was say, you have wave functions, you have the Schrödinger equation, that's all you need. Just believe in that. Believe that the wave function represents reality. There's nothing else other than the wave function. And there's no collapses, no measurements, no observations. All the wave function ever does is obey the Schrodinger equation. That's what he said. So just to contrast, here I told you, this is the old-fashioned textbook version of quantum mechanics, two different sets of rules, right? When you're not looking, when you're measuring, Everett says, here are my rules. There's one set of rules, and they apply all the time. And the rules are that they're wave functions and they obey the Schrodinger equation. That's it. So this is now called the Everett interpretation of quantum mechanics. And then he left the field. Never had an academic job, worked in defense analysis, and died at a young age, at about my age now. He drank and he smoked a lot, and he messed around. He was a brilliant, brilliant guy, but he could not handle the academic lifestyle, so he lived a different lifestyle entirely. This is his legacy. Erase all those rules, see what happens, okay? The Everett interpretation of quantum mechanics. It's not an interpretation in any sense. That's a very old-fashioned, useless word in this context. It's a theory of physics. It says this is the world, let's make predictions using it. But look, the people who invented the Copenhagen interpretation were also not dummies. They knew that they had wave functions in the Schrodinger equation, and yet they saddled quantum mechanics with all these extra rules about observations. Why did they do that? Why was this not obvious from the start? So to get there, let's turn to the thought experiment stylings of Erwin Schrödinger, and this is the Schrödinger's cat thought experiment. And I presume that you've seen some version of this before. There's a box, there's a cat inside. The goal of the experiment is to take what everyone accepted as true, namely that tiny quantum mechanical systems could be in superpositions of different possible observational outcomes, and amplify the superposition to the macroscopic world, to a cat. A friend of mine once talked to Erwin Schrödinger's daughter, and she said, I think my father just didn't like cats. So in the experiment, there is a radioactive source which has a decay amplitude, which means that the source will have a wave function that becomes a superposition of I've decayed and I've not decayed. And there's a Geiger counter, a detector, which goes into a superposition of I've detected a decay, I have not. I've clicked and I have not, okay? If the Geiger counter clicks, it opens a little container and lets gas fill the bigger box. In Schrödinger's thought experiment, the gas was cyanide, and so the cat evolved into a superposition of alive and dead. In my version of the thought experiment, it's sleeping gas in the little box. The cat evolves into a superposition of awake and asleep. It's just as good for thought experiment purposes, and no thought experiment cats need to be harmed. And the reason why Schrödinger did this, again, he did this in correspondence with Einstein. They wrote back and forth, and he eventually wrote a paper about this. He was not trying to say, like, isn't quantum mechanics awesome? Like Jeffrey said in his quote, he was a little chagrined at what quantum mechanics had turned into. So what his thought experiment was meant to show you is, surely you don't believe that. Surely you don't believe that. I mean, classically, sure, maybe there's an alive cat or awake cat or an asleep cat, but I just don't know. That's always possible. Maybe I just don't know something classically. But the formalism of quantum mechanics says that in the box, there is literally a superposition of an awake cat and an asleep cat until you open it and you look. And Schrödinger's like, come on, gang, we got to do better than this. So just to go through, what would you say in the Copenhagen textbook version of things? And one of the moves that is made in the Copenhagen way of talking is very fishy right from the start. Namely, you treat your little quantum mechanical system using the rules of quantum mechanics, but you treat observers classically. Even though they all knew that observers, like human beings, were made of atoms, and atoms obey the rules of quantum mechanics, for some reason, left slightly murky, observers were supposed to be treated classically. Why? Well, that's because it works. So here's a picture of Niels Bohr as a classical observer, and I'm putting classical things in square brackets, quantum things in parentheses. So the combined system, before you open the box, is that the cat is in a superposition of awake and asleep. The observer has not yet looked at it. The observer opens the box. The wave function collapses when you observe it. And then either the cat's awake and the observer saw it awake, or the cat's asleep and the observer saw it asleep, okay? That's what we tell our students to believe. No questions are permitted at this time. So what would you say if you were Everett, or if you just didn't believe in all this collapsing stuff? Well, Everett actually called his theory the theory of the universal wave function, because he understood that, I may feel classical, but I should obey the rules of quantum mechanics just like everything else. It's not fair to just treat me as classically. So he says everything is quantum, okay? So that means there's a wave function that describes both the cat and the observer at the same time. And here we start, there's Hugh Everett, the observer. We start with the cat in a superposition and the observer has not yet looked. And then the act of measurement is not a mysterious, weird thing. It's just you solve the Schrodinger equation. You solve the equation and see what happens. And what happens is the cat becomes entangled with the observer. And the wave function of the whole system evolves into a superposition of the cat was awake and the observer saw the cat awake, plus the cat was asleep and the observer saw the cat asleep. Now, the reason why this isn't obviously true, it's true but not obviously so, is because no one has ever felt like they were in a superposition. No one has ever done this experiment or the equivalent. No one has ever done this experiment that I know of. But they've done similar things. No one has ever said, oh yes, I feel like I'm in a superposition of seeing the outcome in different ways. You always perceive a definite measurement outcome. That's a puzzle. Well, what can we do about that? Well, I did cheat a little bit here already, because I told you the wave function should describe everything in the universe, and then I only put a cat and an observer. Technically, I should put everything else in there as well, right? And like all the air in this room and all the light coming from the photons coming from the lights and so forth. That's hard to keep track of, so we bundle all that stuff up and we call it the environment. So we have a cat, we have the environment, we have an observer. Okay, that's a more honest description of what's going on. And the reason why it matters, because classically it wouldn't matter at all. So in the box where the cat is, there's air molecules bumping into the cat. Who cares? They're not going to affect it in any obvious way. But in quantum mechanics, the state of those air molecules will depend on whether the cat is awake or asleep. Because there's a molecule that might hit the cat if it's awake and climbing around the box, but miss it if it's asleep. This is the phenomenon called decoherence. The quantum system that you care about becomes entangled with its environment, and you can show this happens very, very, very fast, almost instantaneously. So right away, before the observer does anything, the cat and the environment are entangled with each other, and then the observer opens the box, does the measurement, and then you get an entangled superposition once again. Cat's awake, environment saw the cat awake, observer saw the cat awake, plus cat's asleep, environment saw the cat asleep, observer saw the cat asleep. I'm not sure, you might think to yourself how that helps things. I've added an environment, I still had this puzzle. I've never felt like I'm in a superposition, but there I am twice with two different states of the cat going on. What's going on? So here's the same thing again at the top. This is the state that we're trying to think about. And what Everett pointed out, his single genius move was to say, look, subsequent to this, once this has happened, nothing that ever happens in the first part of the wave function, the part where the cat was awake, has any observable impact on what happens in the other part of the wave function. And you can show this mathematically because precisely the environments are very different from each other. That these are what we call branches of the wave function. There's a branch where the cat's awake, a branch where the cat's asleep, and Everett says it's as if they've become separate worlds. Before, there was one world and the cat was in a superposition. After, there are now two worlds that go their own way. So his explanation for why you've never felt like you've been in a superposition is because you haven't been. Rather, there are two of you. There's one that saw the cat awake and one that saw the cat asleep. When you identify you in the wave function, you're in one of the branches, not in all of them simultaneously. It was a little philosophical move that he made. And this is why the Everett interpretation is called the many worlds interpretation. And the thing to point out about this is, at no step in the argument Did we say, you know what would be awesome is if there were like a million worlds? If there was like a multiverse, like dude, that would be great. That was never part of the idea. All we did was follow the formalism of quantum mechanics to see what it predicted. And what Everett is saying is, what it predicts is exactly what we see. And as a consequence, there's all these other universes that we can't see, but who cares? It does actually describe the world that we do see. Isn't that why we're here? Not everyone agrees, apparently. So there are objections, and there are good objections and less good objections. I'm only going to tell you the bad objections to the many worlds interpretation, only because I don't have enough time. I'd be happy to tell you the good objections, or you could buy my book, Something Deeply Hidden. They're explained there. So the most obvious objection is, that's just too many universes. I don't like it. This is the most common objection, and between you and me, I think this is the only objection. I think this is the objection everyone really has when they don't like it, even if they offer you other objections. I think they just don't like the idea that there's all these other universes out there. But look, you can easily believe that an electron can be a wave. You better have to believe that if you want to explain atoms and so forth, and the double slit experiment. That means the electron is in a superposition of possible measurement outcomes. And if you have two electrons that can be entangled, you better be able to believe that two electrons can be in superpositions. And once you go from 1 to 2, it's trivial, you can ask your local mathematician, to say that the universe can be in a superposition of different possibilities. That was always there in quantum mechanics. Everett didn't put that in. The possibility of a superposition of many, many worlds was always there as soon as you knew that there's only one wave function for multiple particles. The only question, the worlds were always there. Every version of quantum mechanics has enough room for all the worlds. The only question is whether you let them be real. As a friend of mine, Ted Bunn, once said, it's not that Everett is the many worlds interpretation, it's that every other interpretation is the getting rid of worlds interpretation. The worlds are there. Another objection is, this can't be tested, can't be falsified. Well, I have a simple response to that. Yes, it can. It's very easy to falsify it. Remember, the theory doesn't start by saying there are a lot of worlds. The theory says two things. There's a wave function, it obeys the Schrodinger equation. You could easily falsify that. You could falsify it by showing there's something in addition to the wave function. There are theories like that. You could also falsify it by showing that the wave function doesn't always obey the Schrodinger equation. And there are literally experiments going on to do exactly that, because there are theories that say that. So they're trying to falsify it. They might do it. That means it's falsifiable. That was a little philosophy there. I hope that didn't go too far, too quickly there. But it's exactly a good scientific theory. Now, admittedly, it predicts things that you can't observe. So what? Every theory does that. You don't judge a theory by what you can't observe about it. You judge it by whether it fits the data. Another objection is, where does the energy come from to make all of these worlds, right? Like, there's a lot of stuff in the universe. You're telling me it's getting duplicated all the time. That seems like it would cost a lot of energy. So here's a little picture of the evolution of the wave function of the universe from bottom to top. Time is running from bottom to top. The point is that there are more and more worlds, but they're not created equally. They can't be, because you have to predict a probability for measuring different things. And the way that comes into the formalism is that different worlds have a different oomph, a different thickness, okay, a different weight. And that is reflected in all the quantities associated with that, including their energy. So this is one of the objections where, if you know the math, it's 100% straightforward to be reassured this is fine. Energy is conserved. In fact, arguably, the Everett interpretation is the only one where energy is conserved, but the energy that is being conserved is the energy of the wave function of the universe. You don't get to see it. You live in a universe, and your universe is getting thinner and thinner. It is giving less and less of a contribution to the energy of the whole. But you don't notice because, here's the good news, you are getting thinner. At least in the wave function of the universe. The relative size of you and the rest of the universe remains the same. So as far as you can tell, the universe has the same energy in it all the time. But secretly, the amplitude of your universe is getting less and less as time goes on. Okay, And then there's the more psychological objections, like, again, it's a kind of a version of the first objection. Like, you're telling me that I am not a single person. You're telling me that there are parts of me that see the cat awake, even though I saw the cat asleep. I would like to talk to them. I have questions, right? Does this mean like there's a version of me that did ask her out on a date in high school, right? Like, how did that world turn out? This is just bad metaphysics, is the answer. Once the branching of the wave function of the universe occurs, the different copies of you are different people. They're not a part of you in a different universe. They are almost exactly analogous to identical twins, okay? An identical twin starts out as a single fertilized egg, a zygote, right? Only one of them, and then it splits apart, okay, into two separate people. And even though those two separate people were once a single cell, nobody is tempted to say, it's okay if one of them dies, we still have the other one. They're not two parts of the same person, they're two separate people. They're similar, they share a common history at some point, but they're two separate people, and the same thing is true for you when the wave function of the universe branches. The only difference is you can't talk to all of your almost identical twins in the other universes. And what this means at the practical level is there is really no ethical or moral or philosophical impact to all of these extra universes that would be any different than the ordinary textbook Copenhagen interpretation of quantum mechanics would let you talk about. The fact that there are many copies of you, but all of them have different amplitudes, gives you the same utility function or whatever you want to have as you would in a universe where you could just probabilistically predict experimental outcomes. Okay, so by now, you're convinced it's the right answer, right? Everett, many worlds, you're good, you're on board with that. But look, at heart, I'm still a physicist. I still want to do science with this. It's good to know, it's more than good, I don't want to downplay it. It's crucially important to understand what is really going on in these circumstances. But it's not just to make us feel better. It's because a good understanding of what's going on at the fundamental level will lead to better physics. Physics has learned a lot about the functioning of the universe, but there are still questions that are not answered. Maybe if we understood quantum mechanics better, we would be better at answering them. So Everett in particular faces a challenge that other interpretations don't. There are competing views against the Everett interpretation, and they're perfectly respectable, taken seriously by very, very smart people. But I think that it's accurate to say that other than the Everett interpretation, every other attempt to make sense of quantum mechanics smuggles in some classical structure somehow, whether it's space or locations or forces or particles or something like that. There's something we're familiar with from the classical world that all these alternatives to Everett take for granted. It's only in the Everett interpretation that you say there are wave functions and they obey the Schrodinger equation, and that's it. There's no room for extra stuff. So in particular, there's no room for space or fields or particles or any of that. It has to be derived. It should emerge from this deep underlying explanation. So the challenge to an Everettian, and this is what I actually was referring to as one of the real puzzles about Everettian quantum mechanics, is to start from a purely quantum mechanical description of the world and explain why the world that we see looks so classical, looks like stuff with locations in space. Why is that? That's a puzzle that every other interpretation just puts in by hand. But given lemons, we make lemonade. This is also an opportunity because, like I said, there are unanswered questions in physics. The biggest, most looming one is how to reconcile gravity with quantum mechanics. You may have heard of gravity, one of the famous forces of nature. Isaac Newton found the apple falling, etc. It was really perfected by Einstein, again, smart cookie, where he said that gravity is the curvature of space-time, is an intrinsic feature of space-time itself. It's one of the forces of nature. There are others, electromagnetism, the nuclear forces. With those other forces of nature, we have a procedure. We start with a classical theory, and we quantize it. okay? We have a literal set of rules for taking a classical theory and turning it into a quantum mechanical theory. Nature doesn't do that. That's not how the universe works. The universe doesn't start with a classical theory and turn it into a quantum theory. It just is quantum mechanical from the start. And what we notice is when we take Einstein's theory, general relativity, his theory of gravity, and try to do these rules of quantization to it, it doesn't work. So people invent other options, string theory, loop quantum gravity, and so forth. And all of them have been interesting and have had some partial successes. None of them has been clearly the right final answer. But again, nature doesn't do that. So maybe the mistake that we've been making is trying to quantize gravity. What we want is a quantum theory that gives us gravity. We want to try to find gravity within quantum mechanics. And this is a task for which the Everettian approach that has no classical presuppositions in it is ideally suited. So let's see if we can do that. I mean, yes, a little bit, otherwise I would not be telling you this, but this is absolutely like speculation from here on, where this is research that is ongoing, might crash and burn at any time, but it's an interesting thing to think about. So here's young Einstein coming up with the idea of general relativity, and it's a very simple idea. Gravity is the curvature of space-time. That's what gravity is. He was inspired to come up with this, noting that you couldn't tell whether you're in a gravitational field or just being boosted at an acceleration like on a rocket ship. Because unlike all the other forces of nature, gravity acts universally. It acts the same on everything. So maybe it's a feature of space-time itself. He even came up with an equation. There it is. Again, not going to explain that. But the meaning of it is that the geometry of space-time is influenced by the amount of energy, the amount of stuff. Okay? So a planet, galaxy, dark matter, curves space-time in some particular way. If you want to know what all those symbols mean, do I have the book for you? I mean, no, I don't have it, but it's coming out soon. Biggest Ideas in the Universe, Volume 1 will come out in September, and I will go through all the equations starting from no knowledge whatsoever. So if you don't know calculus, you will learn Einstein's equation and what all those symbols mean by buying this book. I mean, you could pre-order it like right now. So we want to know, can you find this structure? Can you find space-time being curved under the influence of energy just within quantum mechanics? Well, it's okay to take clues from what we know. Okay? What we know of the forces of nature that we do understand is that they are described by quantum fields. They're not really particles. They look like particles in the right circumstances, but they're really fields at heart. Like the magnetic field here is a picture. A field is just something that has a value at everywhere in space. And what that means when you get to quantum mechanics is even empty space is kind of a fun, exciting place. Okay? If the world were really particles, then there would be particles at certain locations and nothing interesting going on in between them. It would just be empty space, just space sitting there. Whereas in quantum field theory, every location in space has a bunch of quantum fields. If you think that space is empty, all that really means is the fields are in their lowest energy possible state, what we call the vacuum state. If you think that there are particles there, that means the fields are vibrating a little bit more. It's all a different thing the fields could be doing. So empty space is not empty in quantum field theory. And we also know something about empty space in quantum field theory, is that there's a relationship between the different regions, namely they're entangled with each other. So we have different regions of space. This picture is supposed to be space cut up into little subregions. Every subregion has little quantum fields vibrating in it. And what I'm pointing out is that the different regions have quantum fields that are entangled with each other with a very special structure. The closer the regions are, the more entangled their fields are in empty space, in the vacuum. So if they're nearby, lots of entanglement. If they're far away, very little entanglement, right? Again, this is a feature of standard ordinary quantum field theory. We don't, in this path that we're trying to take here, deriving everything from the wave function, we can't help ourselves to words like distance. But we can help ourselves to words like entanglement. So let's turn it around. Rather than saying, I know how far away these regions are and I can derive how entangled they are, let's say I know how entangled these things are. Let me define that to be a way of measuring distance. The closer together, the more entangled two parts of the wave function are, I will call them closer together. That is a way of imposing a distance, a measure, on this purely quantum mechanical structure. And then if you know the amount of entanglement between two parts of the wave function, and therefore you know their distance, you know the entire geometry of space. Someone like Euclid or Gauss or Riemann would be very happy. The famous mathematicians who talked about geometry, you can derive an emergent geometry just from entanglement within a quantum wave function. So there's a relationship. Geometry is related to entanglement. There's also a separate relationship that entanglement is related to energy. Remember, I said in the previous picture here, where it was all light blue, this is the vacuum. This is empty space, nothing happening. To put energy there, to put particles there, I need to break the entanglement. I need to decrease the amount of entanglement between one region and its neighbors. So there is automatically, in quantum field theory, a very natural relationship between energy and entanglement. And again, we can go the other way around. When you have less entanglement between one region and nearby things than you would in the vacuum, you say, I have energy there. That's meaningful. And so we automatically have this relationship that given a bunch of entanglement within some big quantum wave function, we can both derive a geometry of space from that and assign an amount of energy to different locations in space. And they're related to each other with an equation. But that's exactly general relativity. This is Einstein's theory of gravity, that space and space-time naturally have a geometry, and that geometry is influenced by energy, mass, momentum, all of that stuff. So we can at least imagine an alternative history of physics where general relativity wasn't invented until long after quantum mechanics, and people said, you know, given what I know about quantum mechanics and given what I think is probably true about geometry, I bet that geometry is actually not static. I bet it's dynamical in response to the amount of matter and energy in the universe, and you would invent general relativity that way. So anyway, this is what my friends and I are working on right now. This is very, very tentative. I've sold you a bill of goods. I've not told you any of the possible stumbling blocks or loopholes in this. It's not a finished project yet, but the point is, the initial indications are extremely promising. Rather than starting with strings or loops or causal sets or what have you and quantizing them, just by starting with a quantum wave function and asking, what are the natural ways where space and time could emerge, you get something that naturally looks like Einstein's theory of gravity. We're far away from getting the complete picture, but it's absolutely worth working on this to push it forward in new directions. Or, as I like to say, it is time to climb out of the box. This is Caliban here, and Caliban, thanks you very much for coming tonight.
If anyone has any questions, please raise your hand. My colleague and I will pass a microphone around. Over there. Please.
It's dark in here, so you got to raise your hand vigorously.
Thank you for that mind-blowing discussion. Have you or any of your colleagues who support the many worlds approach been able to hypothesize a classical way of testing or showing it, or is that impossible?
I don't even know what you mean by a classical way of testing.
Well, I assume you can use mathematical equations that might point in the direction of this. And I'm just wondering whether, as a layman like me, sees the world, can you or any of your colleagues imagine an experimental way to demonstrate that, yes, there really are multiple versions of me, and one of us has a dead and one of us has a live cat?
So the point is, quantum mechanics says that. If you don't like it, you can change the theory. And people do. There are theories that are very viable right now with hidden variables. There are theories where the wave function does not always obey the Schrodinger equation. There are other kinds of theories that work in various ways to get rid of the other parts of the quantum superposition. And they're testable. You can observe these in principle. They haven't seen them yet. So my bet is going to remain on many worlds. Where are we? Okay, go for it.
Can you talk about the experiments like G2 and the next phase of LHC and kind of the discrepancies there and how that might, like the future of experiments?
Sure. So let me rephrase the question. There is, of course, I've been very unfair to my friends in the physics community when I said, like, they came up with a story in 1927, they've been sticking to it ever since. I could be much more vivid about what was going on. There were literally memos passed around in the major physics journals saying, do not consider papers on the foundations of quantum mechanics. There were people who were making major contributions to the foundations of quantum mechanics, like John Bell at CERN, who wouldn't tell anybody that he was working on it. He hid his work on this subject, okay? Why? Again, it's not because they were dumb. They had other things to do. They were working on things like quantum field theory and particle physics and nuclear physics that were testable in a very direct, immediate way. And that is still an ongoing project. For better or for worse, the situation is we've been too good at it. We have a model called the Standard Model of Particle Physics, which is literally compatible with every experiment ever done in a laboratory here on Earth. That's a terrible situation to be in as a physicist because it's very hard to make progress when the data agree with your existing theory, especially when you don't think that theory is right. You don't think the Standard Model is the final answer. It doesn't include gravity, it doesn't include dark matter, it doesn't understand or explain what happens at the Big Bang, and so forth. There are, and finally getting to your question, there are, and there always have been and always will be, anomalies. We do many, many experiments in physics all at once. Roughly speaking, they all fit the Standard Model, but if you do enough experiments, just by chance, some of them won't, okay? And these anomalies sometimes go away, but then the few that don't upset the apple cart and really teach you new physics. So there are new anomalies, especially with muons. There's two different anomalies, both with the spin of the muon and with the decay of the muon. The muon is one of the elementary particles, a heavier cousin of the electron. The muon seems to be misbehaving just a little bit. Now, we don't know whether the misbehavior is just our experiments aren't good enough or whether or not it's really a sign of physics beyond the Standard Model. We just have to wait and do the experiments better. And the outcome of those experiments will have absolutely zero impact on anything that I said today. Because they all just depend on quantum mechanics being right. And again, quantum mechanics works. Copenhagen works. It makes the right predictions for experimental outcomes at particle physics experiments, and that will almost certainly continue to be the case in future particle physics experiments. One of the reasons why thinking about the foundations of quantum mechanics has become more popular is because there's other kinds of experiments where the Copenhagen interpretation is not that it's proven wrong, but that it's just not up to the task because the dividing line between classical and quantum becomes fuzzier. When you make quantum computers, when you put lots of things into entangled coherent states at the same time. This is not what particle physicists do. Particle physicists just use and abuse quantum mechanics for their own purposes, but they don't care about the foundations of it, and their experiments are going to help us with it.
I'm just trying to figure out how to fit consciousness into this whole thing, and I don't know if you're willing to, to talk about that or even go there, but it seems to me that that Everett's theory would work well with that, because as everybody follows on their path in a universe, and we each have our individual universe that we're living in, and so would that be a way to kind of approach this, to figure out the dualism part of it?
Yeah, no, Everett's theory is very, very clear that quantum mechanics has absolutely nothing to do with consciousness. That's the relationship. The branching of the wave function in multiple possibilities. Remember we had the measurement problem in Copenhagen interpretation. Does it somehow involve consciousness or agency or anything like that? In this theory, the answer is no. It's decoherence, which happens before the agent even looks at the thing. It has nothing to do with consciousness, thinking, anything like that. That doesn't say that it explains consciousness. It has nothing to do with it. So the puzzles and the prospects for understanding consciousness are exactly the same in Everettian quantum mechanics as they would be in Copenhagen or in classical physics or anything like that.
This is also a consciousness question. So Max Planck said that in his view, consciousness was fundamental and that matter was derivative from consciousness. I'm guessing you disagree with that, and so my question would be, what do you think he was missing? What did he get wrong, and why might he have said that?
Sure. Look, Max Planck said a lot of dopey things. He never believed in photons, okay? If you're looking for wisdom from physicists 100 years ago, you should do better than that. I think that it was, to be more fair, there was a time, in between, let's say, 1927 and 1957, when it was perfectly reasonable to think that there might be some relationship between conscious observation and quantum mechanics, because there were two separate sets of rules, right? And one of those sets of rules, if I can find them, involved the word measurement. So what does that mean? Maybe it involves somehow consciousness. But we know better now. And it's not just Everett. Bohmian mechanics, spontaneous collapse models, a whole bunch of other approaches to quantum mechanics are 100% physical and materialistic. They've removed consciousness from the equation. There's still a lot of old quotes from dead physicists that would tell you otherwise, but nowadays we should do better.
Hi there. Thanks so much. Earlier, you showed a graphic of, the universe splitting as branches on a tree and so forth. That picture implies that there is an original world state. So what can you say about that original world state and, I suppose, entropy?
Yeah, no, very, very good. You've noticed that, I don't know what is going through your brain here, but if you look at, where'd it go? This equation doesn't tell the difference between the past and the future. It has no directionality in time. It works equally well. It's just like Newton's laws of mechanics. Do not pick out a direction, forward or backward, okay? So like I told you, the whole Everett interpretation is just the Schrödinger equation and nothing else. But the Schrödinger equation has no directionality of time, but this picture definitely does. There's an obvious difference between the past and future. What's going on with that? What's going on with that is, by my first book, From Eternity to Here, where I talk about the arrow of time and the fact that it is not dependent on the laws of physics from moment to moment, but on the initial conditions of the universe. There is a cosmology problem, which is another open problem and we don't have the answer to. Some of us have ideas, but there's no consensus, about why the early universe was in a quantum state, which by all rights is unusual, is strange, is not random, is not generic, is not what you would expect. It's very, very special. Why? Some of us have ideas. Stephen Hawking thought he knew the answer, but we don't know. So it's a great question. We don't know the answer. What we do know is, if you make that assumption, if you say that for whatever reason our observable universe started in a state that is very special, highly entangled, low entropy, or highly unentangled, I should say, then it all happens. Then it all fits together. It all branches like this very, very naturally.
Over here.
Can you explain explain how theoretical physics is informed by experimentation currently? It sounds like part of it is blackboard and chalk and talking to each other. What and how do you come up with experimentation?
Yeah, so I mean, this is a great question, and it depends a lot on what kind of physics you're talking about. I mean, let's be clear, the kind of physics I've talked about here in this talk is a tiny sliver of physics overall. Most physics is in a state where theory and experiment are closely connected with each other, whether it's atomic physics or materials physics or biophysics or whatever. But there are times, like I said, with the standard model of particle physics, or in some sense, what you might call the standard model of quantum mechanics, the Copenhagen interpretation, where the theory does a good enough job fitting the data that you don't have experimental clues as to how to go beyond it. We still look. So the point of that it being in most theoretical physics, very, very closely connected with experiments. In places like the foundations of quantum mechanics, there still are experiments going on. This is an experiment, you see the year here, 2020, this picture of an actual experiment looking for wave functions collapsing in violation of the Schrodinger equation. And if they find it, that will falsify the Everett interpretation of quantum mechanics. There are, again, the problem is the theory is too good. So I've made experimental predictions about energy conservation and things like that that seem to be predicted by quantum mechanics, but there's no competitor to quantum mechanics overall, right? It's not like we're comparing quantum mechanics to something else. So we're just trying to think of the best conceptual framework in which to think about quantum mechanics itself, and for better or for worse, that's a lot of scribbling at the blackboard. That's what's involved until we get some good ideas that can be compared in the lab, like these are today.
I think we have time for one more question. One more.
One more question, one really good one. There's one right there.
I was just seeing that the James Webb has, has seen back 13.7 billion years, and it's just amazing. Could you just talk about that? Can it see the Big Bang or something like that?
Sure. No, it cannot. But that's okay, because we already saw the Big Bang back in the 1960s. The cosmic microwave background is the leftover radiation from the Big Bang. Now, sadly, the cosmic microwave background only gives us a view of what the universe looked like 380,000 years after the Big Bang itself. The earliest galaxies will always be later than the cosmic microwave background. The moment the microwave background radiation, for those of you who don't know, suffuses all of the universe. You see it in every direction. When I was your age, we had television sets that had antennas on top, and you could pick up, you could get fuzz, you get static from the cosmic microwave background on your TV set. And it is left over from the fact that the early universe, about 14 billion years ago, was a hot, dense state that was glowing. And it was opaque, and it didn't become transparent until 380,000 years after the Big Bang, and we see the radiation that last interacted at that time. What we see when we look at that is it's very, very smooth. In any one region compared to any other region, the amount of energy density or matter is the same, 1 part in 100,000. So there were no galaxies back then. There were no stars, there were no planets, no black holes. All of that stuff, we think, we're pretty sure, grew through the force of gravity, taking the slightly overdense regions and pulling more matter into denser and denser things until you could call them stars and galaxies. But we almost have enough data to say definitively that that had to happen after the microwave background. So we'll learn a lot about galaxy formation, which is very important. You know, like not all of physics is what happened at the Big Bang and what is quantum mechanics. How did galaxies form is super duper important physics, just like what kind of exoplanets are there is super duper important physics, and the James Webb Space Telescope will absolutely help make discoveries there. It will be other kinds of things that get us closer to the Big Bang.
Okay, could we have one last round of applause for Sean Carroll?